Hmm, at least one of these should work for what I need, but which one? I have no documentation from any of these, and I'd like to get an idea of their relative torque. No problem, I just need a dynamometer like this one. However, these things are typically sophisticated and very expensive. This one is about as cheap as they get at around $1,100 with shipping, but obviously still far out of range for a hobbyist. Most are many times more expensive than that. I do like this model though, with a handy button to call the police. Not sure why that's needed in a dynamometer, but I've never actually used one, so maybe it's important. Anyway, back in the real world, most people seem to use some form of a Prony brake to estimate dynamic torque. There are many approaches, and while looking through various sources, I happened to find this short 5-minute video, which proved to be really intriguing and uses a unique approach. It is unique since it was granted a U.S. patent in 2014. It uses a compact set of bevel gears to transmit the angular rotation and measure the force exerted at the end of the lever arm. That brief video by Jeffrey Height is well worth watching, and I've included a link to it in the description below. So my plan was to make a device following closely on his original design. I wanted to collect data on each analysis, so I included a speed sensor, a load cell to measure the force, and I added a linear drive providing compression as a theoretically reproducible brake. These parts were then mounted on a single-channel 4040 aluminum extrusions. The gears were designed as spiral bevel gears to reduce noise and vibration, and they printed without problems. There are 4 gears in the assembly, 2 side gears fixed to the input and output shafts, and the 2 torque gears in the middle with bearings allowing free rotation as shown on the right. Note that the 2 outer gears are left-handed, whereas the central gears are right-handed and mesh properly. 2 half-inch ID sealed deep groove bearings were pressed into the middle gears, and those same bearings were used throughout the system as needed. The parts were 3D printed, and other than the gears, were all pretty simple. I assumed the PLA would be sufficient for these parts since the expected torque was low, but the right-hand shaft should experience both lateral and torsional stress, with perhaps some frictional heating, so that part was printed in ASA. Once everything was printed, the device just needed to be assembled. Starting at the left end, the input gear and shaft are mounted in the first support stanchion. There is a hex shape on the end of the input shaft that matches with one of several fittings for mounting to motors with different shaft diameters. Then the 2 central stanchions supporting the lever arm are put in place, and the lever arm is installed between them. All supports use the same bearings as are used in the gears. That shiny spot on the input gear is a small magnet. Originally I installed a Hall sensor to monitor RPM, and that worked fine at first. But as the stress on the motor increased, the RPM readings went berserk and began showing very high values. I believe that was probably caused by an increase in the motor's magnetic field that overpowered the sensor, so I changed to an optical speed sensor, which has worked fine. Since the magnet was already in place, I just left it there. Those 3 extra bearings at the back of the lever arm are just there and added as ballast to help balance the arm, which is longer and therefore heavier forward than fulcrum. After adding another support for the output rod, the braking assembly is added. That part has an oversized through hole with a thin silicone lining for contact with the rod. The hole is compressed by the linear driver. Finally, the optical sensor with a 20-slot wheel was attached to the end. Adding the strain gauge was simple but took a while since the attachment screw was under the platform, so it had to be aligned. Then the platform moved to fasten it, then moved back and checked, and so on, in an iterative process basically. No problem, just a little time consuming. The last part needed was the mounted linear drive. This uses a tiny NEMA 11 stepper motor, but it has more than enough force for this system. This is aligned with the back of the flexible tab that constricts the rod as it is pushed forward. This is a close-up of the mounted strain gauge. I originally used a 10 kilogram load cell, but switched to this 5 kilogram version since the forces are pretty low. And this shows the back of the compression assembly. The output rod passes through the central hole with free clearance, which is gradually reduced as the linear drive advances, and provides the friction resistance to the system. The stepper is controlled by this integrated device. I used mode 7 option, so while the counterclockwise button is held down, the motor advances at 20 RPM. When the button is released, the current position is maintained for 6 seconds, and then the drive quickly retracts at 60 RPM. These values are all pre-programmed into the controller. Finally, this is a simple optical speed sensor. These are dirt cheap and easy to wire up. The wheel with 20 slots is screwed to the end of the shaft. Only 2 sensors are needed for the system. The optical sensor just requires wiring its output to one interrupt-enabled digital pin, and the load cell uses a standard HX711 Wheatstone bridge amplifier. I used a Nano Every for the microprocessor here. The Arduino program is quite short and just monitors the current speed and force from the strain gauge once every second, and then sends the data packet out the serial port. The load cell calibration was made by using a set of 7 weights to calculate a factor of 190.5, which was then inserted in the program. To test the system, I chose the 2 gear motors shown here, with different voltages and speeds. To begin, I first wanted to check the accuracy of both the speed and force readings. To monitor the output, I wrote a simple Windows program that just read the serial data from the Nano every second and added it to a list box. I also plotted the speed, force, and estimated torque in real time. Since it's hard to read the values in this video, I've superimposed the output here. In this speed test, the 24-volt motor was run at about 12.2 volts and produced about 238 RPM. Checking that with a laser tack reading off of the shiny magnet gave the same value. Increasing the voltage to 20 resulted in a speed of about 419 RPM, which again agreed well with the laser tachometer, so speed measurements seem to be okay. To test the load cell, I just reweighed the same weights used for calibration, with the reported results now based on the calibration factor, and those values remain good. This shows the observed values from the measurement of the last 2 weights, and those values of 20 and 50 grams agreed perfectly. So this is the evaluation of the first motor, running at 24 volts and a nominal 600 RPM. The motor was allowed to run until stable output was confirmed, and then the stepper drive was activated. Because of the offset, it takes a few seconds for the drive to make contact with the pad, at which point resistance begins. The readout on the power supply is not super accurate, but it's probably good enough for this purpose. and shows that the baseline amperage is about 100 milliamps, and then as resistance is applied, it more than doubled to about 250 milliamps at its peak. For all of these measurements, I plan to run each test in duplicate to evaluate consistency. With this motor, there was a small but definite decrease in speed as the torque load increased. This is the second motor running at its rated value of 12 volts and about 300 RPM. This is a pretty reliable motor, and I've used several of them in per-hour applications. It drew about twice as much current at baseline, and then increased from about 220 to 380 milliamps at the maximum load. Although the ordnance scale is not the same as the previous motor, this one did show less reduction in speed under the load that was applied. My program automatically saves the contents of the list box to file when it is cleared, so the runs can be re-examined later. This shows a reconstructed Excel plot of the two speed and torque curves for these motors. Again, the torque peaks are flat on top, since the maximum frictional force was maintained for 6 seconds before it was released. Torque speed curves can be estimated by plotting the data from just the active resistance area of the plots, which show the expected inverse relationship for these small DC gear motors. The scatter of points at the right end of the plots reflects the variation seen during a maximum loading period. Changing and connecting different motors in the system is very easy, using different printed adapters as needed to mount motors of different shaft diameters. Each motor's analysis only takes about 2.5 minutes, so I'm evaluating a number of motors now to compile data on them, and I plan also to examine some stepper motors with the same system, using a different powering arrangement, of course. I found this little project to be fun and informative. I hope you have found it of some interest as well, and thanks for watching.